Welcome to the EPG Pathashala, the lecture series in computer science for the postgraduate program, and we are on the compiler design module paper module number 35, where we will be talking about loops in flow graphs. The objectives of this module are to understand the peephole optimization technique, to understand the terminologies and concepts involved in loops and control flow graphs. Now, we said that there is optimization can basically happen either at the intermediate code level or at the final target code level, that is at the assembly language level. Now, the previous transformations whatever we have seen in the earlier module talked about transformation that is happening with respect to the intermediate code, and this module we will start with optimization that is possible with respect to the target code as well as the intermediate code. Now, peephole optimization is a classic technique where we will observe a short sequence of instructions, target instructions. Now, this short sequence is typically looked upon through a window, therefore it is called as a peephole, okay. And then using in this particular window, okay, not looking at any global or local or whatever it is. Now, it is very much local in the sense that it is not even with respect to one particular basic block, it is with respect to only a sequence of 4 or 5 instructions. Within those instructions, how much of optimization is basically possible. That is what is called as peephole optimization, where you will try to replace the instructions by a faster or a shorter sequence of instructions wherever possible. Now, it is typically applied to intermediate code or target code, typically to a target code more than intermediate code, because intermediate code already would have taken would have already been done with respect to the other optimization procedures. Now, the typical optimization that is possible with respect to peephole are redundant instruction elimination, flow of control optimization, algebraic simplification, use of machine idioms, etc. Now, the first one is eliminating redundant loads and stores. Now, that is what we have said, redundant instruction elimination, which is consider this instruction move R0 comma A and move A comma R0. Now, this is going to happen, this is going to occur one after the other. I am looking through a small window, therefore, I know that this instruction is redundant, that is the second instruction is redundant, therefore, I will try to get rid of it. The second instruction will be deleted, but only if it is not labeled with a target label, okay. So, of course, if I call this as a target of a jump or a conditional or unconditional jump, I cannot get rid of it, but if that does not have a label, I can basically get rid of this instruction because R0 already has a value of A, okay. So, R0 move R0 comma A, so actually R0 and A has got the same value here itself, therefore, there is no need for moving again A back to R0. So, the peephole typically represents sequence of instructions with at most one entry point, that is one more characteristics which we are trying to look at. Now, the first instruction can also be deleted if live of A is equal to false. Now, this is one more point, that is if the live, because we already said in one of the modules where we will have the liveness information of all the variables. If A is not going to be used, okay, if A is not going to be used, then the first instruction could also be deleted. I can simply have it in register R0 itself, get rid of the, anyway R0 has a value of A computed, right. So, I can get rid of both the instructions and use R0 wherever A has to be used later, okay. So, that is one more one more thing which you can basically observe. Definitely you can get rid of these instructions if it is again not a target of a conditional or unconditional jump, but definitely we can get rid of we can get rid of this also if A is not going to live later. Now, the second one is deleting unreachable code. For example, here this is done at the intermediate code level. So, for example, you have if 0 double equal to 0, go to L2. Now, we know that 0 double equal to 0 is going to be definitely true because it is LHS is equal to RHS. So, therefore, this path, that is the computation of B is equal to X plus Y, is never going to happen. So, what we can do is you can directly convert this into a go to L2, because 0 equal to 0 will be done with respect to in the optimization level itself. I will get rid of this. This will be a simple go to L2. So, I can convert this to a go to L2 and then that will branch, thereby this instruction becomes redundant. I can get rid of this instruction. So this is called as an unreachable code, because at any particular point of time I am never going to follow this particular path, because this will always be true. So wherever things are already defined, already known earlier, I can get rid of that particular path and then choose a path which is going to be necessary for actual computation, and the others can be eliminated completely. So this again can be done only if I have look it through a small window, not bothering about whether something else is going to be computed already or not. The next one is, so unlabeled blocks can be removed. That is what we are trying to look at here. The next thing is called as branch chaining. This is also going to be optimization based on flow of control. Okay, so because we said the Peephole optimization, the first one is redundant instruction elimination, eliminating redundant loads and stores. Second one is flow of control optimization, where one flow, which is what we have already talked about, deleting unreachable code. The second flow of control optimization is this branch chaining. For example, here if A is equal to 0, go to L2, else you come to this particular scenario. Okay, so where again L2 will be defined here, okay, and L2 says simply go to L3. So this is branch within a branch. So I come to this position. What I see there, I don't see code. I simply see a go to L3. Now rather than that, what I can do is I can get rid of this block. Okay, I can get rid of this block and rename this as go to L3 rather than going to L2. That is going to L2 and then from there branching, rather than that. That is, this branch will be done and then I'll have to go to L3. I can get rid of this and say if A is equal to 0, directly go to L3 itself. Therefore this block, that is the statement go to L3 with a label L2, can basically be removed. This is called as branch chaining removal. Okay, of course here this is required because there is a possibility that A may not have a value of 0. Okay, that is why this is required. Now this block doesn't have anything other than a go to L3, therefore I can get rid of that and I can replace in place of L2 with L3. Okay, shorten the length of branches by modifying target label. That is the situation for branch chaining removal. Then next one is flow of control optimization. Again, remove redundant jumps. This is similar to the previous one only. I have a go to L1 here. Okay, so where L1 is going to be starting as a simple block. Now rather than that, I can combine both together. Okay, anyway, even if there is no go to here, after this instruction, this is going to follow. So I can combine these two into a single block itself and avoid this go to L1. So this is one more flow of control optimization. The next one is algebraic simplification, and this is in the context of use of machine idioms. So A is algebraic simplification and use of machine idioms. So reduction in strength is what is done here. A is equal to x power 2 and B is equal to y divided by 8. Now x power 2 is nothing but x into x. Okay, I am replacing power computation by a simple multiplication, and this is y divided by 8. Now division by 8 is nothing but right shifting by one position. Okay, dividing by 2. So dividing by 8 will be right shifting by 3 positions. Similarly, multiplication by 2 is left shifting by 1 position. So I can use that logic to compute division as well as multiplication if I am dividing it by a power of 2 or multiplying by a power of 2. So I have here B is equal to y divided by 8, that can be replaced with B is equal to y right shift 3. Okay. Similarly, the next one is use of machine idioms, where I have A is equal to A plus 1 here. This can be replaced with an increment function rather than an add function. So I am simply incrementing A. So that can be taken note of here in this instruction. Next one is algebraic simplification, which we have already done earlier itself. The same thing is also done here in the context of looking through a small peephole. So A equal to A plus 0 can be avoided. Okay. And B is equal to B into 1 can also be avoided. I can eliminate these two instructions completely. So A is equal to A plus 0 means adding 0 to A and assigning it to A, which is not at all meaningful. This is nothing but A is equal to A, is nothing but B is equal to B. Therefore, I have eliminated these two instructions and there is nothing in this particular block. Now, the next one, which is very important for further modules are a knowledge of the loops. Okay. Control flow graph can be looked upon as a graph which may contain loops, and these loops are typically known as strongly connected components. Generally, a loop in a directed graph whose nodes can reach all other nodes along some path. Okay. This includes unstructured loops with multiple entry and multiple exit points. So your loops can basically be structured or unstructured, but can have multiple entry exit or single entry. Typically you should have a single entry and a single exit point, but there is a possibility of also having multiple entry and multiple exit points. Now a structured loop is typically called as a normal loop, which has got one entry point and a single point of exit. Now the loops that are created by mapping high level source programs to intermediate representation or assembly code are called as normal loops. Okay. Typically you have normal loops in your piece of code. Goto can create any loop, and break creates additional exits. So if you have a goto jump, unconditional jump like goto, that may create additional loops, and if you have a break, that can lead to a multiple exit points. Okay. So so this becomes break or a continue or a goto will result in creating multiple entry or multiple exit points. So that should basically be identified. Now in this example, I have basic block 1, 2, 3, 4, 5 and 6. Okay. So I have here this example. This is available in the textbook by Ahose Evilman. So control flows from 1 to 2, 2 to 3, and then from 3 I can either branch to 4 or 5. Okay. If I go to 4, I have to again go back to 2 and then start all over from 3. If I go to from 5, I can go to 3 and then I can start all over. So this is one situation. Okay. So what is the problem here? So the problem can be, this is unstructured, okay, where there is a loop 2, 3, 4, that is one loop, other one will be 2, 3, 5, okay, 2, 3 and then 3, 5, that is one more loop. Okay. So whereas on the other hand here, this is very, very clear in the sense that this goes back here, whereas this goes back here. Okay. So multiple entry and multiple exit. So here two proper loops and one unstructured loop here. So the loop 1 is 1, 2, 3 and then going back to this is going to be one loop, and then loop 2 to 4 is one more loop, then loop 2, 3 and 2, 3 and back here, and then coming back to 4 it will be another path. So you have to ensure that your loops are going to be structured as much as possible with a single entry and a single exit point. Now to determine the loops in flow graphs, you have a concept called as dominators. Now why should we do all these things? These are part of the flow analysis, data flow analysis and control flow analysis, which are the next optimization that is possible for any particular piece of code. So we have to construct what is called as a dominator information. Dominators are typically done for basic blocks where it is denoted by D dominates N. I can say, okay, every node in a control flow graph, which is a flow graph, okay, otherwise abbreviated as CFG here, every node is basically consisting of a sequence of instructions. Every node corresponds to a basic block. We can say here node D of a control flow graph dominates node N if every path from the initial node of the CFG to N goes through D. That is, I have to go through necessarily D to reach N. If that is my situation, I will call this node as a dominating node of N. Okay. The loop entry dominates all nodes in the loop, that is the understanding. The immediate dominator M of a node N is the last dominator on the path from the initial node to N. If D is not equal to N and if D dominates N, then D dominates M also. So it is going to be transitive basically. Okay. If M dominates N, okay, if M dominates N, and if you already know D dominates N, then D dominates M. Okay. So D is being dominated by M also. There is one more thing which, one more analogy which you can basically conclude from this dominator representation. Okay, consider this graph. So 1, 2, 3, okay, 4, 5, 6, 7, 8. I have 10 nodes, 10 basic blocks, and this is a cycle here. 1. I can come to 3 either through 2 or through or directly. But in order to reach 4, 5, 6, 7, 8 or 9 on 10, 3 basically has to be reached. I have to reach 3 and get and only then I can come to 4 or 5 or whatever it is. So therefore 3 dominates all other nodes. Okay. Now not only that, okay, let us leave that particular point as it is. Okay, in order to come to 8, node 8, I have to necessarily come through 7. Okay, in order to come to 8, I have to necessarily come through 7. Therefore, I can say 7 dominates 8. Now, in turn, 3 dominates 7. Therefore, 3 dominates 8 also. That is what we are trying to look at as the transitive property. Now, 4 dominates 7. Okay. Now, 5 or 6 is not a dominator node because I can reach, to reach 7, I can come through either 5 or through 6. Okay. And similarly, 8, to reach 9 or 10, I have to come through necessarily 8. So therefore, 8 dominates 9. In addition, 7 dominates 8, therefore 9 is being dominated by 7. So this is converted to a tree representation depending upon what is the, to indicates which dominates which node. So here 1 dominates node 3, okay. So 2 and 3 here, 3 dominates all other nodes, 4 dominates 5, 6, 7, 7 dominates 8 and 8 dominates 9. That is what we are representing as a dominator tree. Now once this is done, it is easier for us to understand what should not be missed in order to do a control flow analysis. So that is why we have doing dominator tree construction. Now we have a concept called as natural loop, where a back edge is an edge A to B whose head B dominates its tail A. Okay. So head B dominates its tail A, and given a back edge N to D, the natural loop consists of D plus the nodes that can reach N without going through D. The loop header is node D. So in this example, this is the loop. Okay, 8 or let us take a small example here. 4, 3. Okay, the loop 3 to 4. This is a natural loop. Okay, so as long as these edges are called as back edges. The one that goes from 9 to 1, the one that goes from 7 to 4. These are called as back edges. So they form a natural loop is what we are trying to look at here. Okay, unless 2 loops are the same header, they are disjoint or one is nested within the other. A nested loop is called as an inner loop if it contains no other loops, and outer loop can also contain multiple inner loops. Okay. So this is one more scenario, and this is the algorithm for natural loop determination. So where each node in a loop except for D is placed on the stack and its predecessors are examined, input will be a typical flow graph, a control flow graph G with a back edge and a back edge N to D, and output will be a set loop consisting of all nodes in the natural loop of N to D. Okay. So this is the procedure. If M is not in a loop, then you form it and push this node onto the stack, and that will be, this is the procedure. What does insert basically do? Insert will, okay, stack empty, well stack not empty, pop this node for each predecessor P of M, insert P, add to it, and then so this will create in the loop L, everything will be created. So as you are looking at the predecessor after predecessor and then trying to insert them into a set, that will be forming a natural loop situation. So here this is a natural loop for 3 dominator 4, okay, and so this is what the smallest, we have already seen this, and this is the one for 7 dominating 10. So 10, there is a back edge to 7. So what will be there in the path? So 7 to 8 and then 8 to 10 and then 10 to 7. So the loop nodes in the loop will be 7, 8 and then 10. So what will be the input? Input will be 10 to 7 will be given here. So I will start with 10, its predecessor is 7, okay, and then 8 will be 10's predecessor is also 8, okay. So I will have 7, 8, 10 as part of my total number of nodes in the inner loop. Now there is a concept called as pre-header and header. So to facilitate loop transformations, a compiler often adds a pre-header to a loop. Now there will be the first basic block is called as a header. Now in addition to that, there is also one more block added just above the header, which we call it as a pre-header. Now the pre-header typically is used for performing this code motion or some strength reduction. It's part of your loop optimization. Because here, if you remember, supposing say I have done some computation here, and if I want to reduce, this is a loop, okay. So this is the target of a jump. So therefore this is a loop. Supposing say one particular expression is computed, and that expression's variables involved in the expression hasn't changed, then it need not be computed every time. Rather, what we can do is we can move that information to the pre-header, where it is computed only once, and the result of that is used here for branching, okay. So that is why we need a pre-header here. So basically you add a pre-header in order to support the loop optimization that is basically required in terms of either code motion is what just now I said, or strength reduction, where you will replace complex computation with cheaper ones, or other possible loop transformations. So in addition to that, we have what is called as a reducible flow graph. A reducible flow graph is what is essential, and that is called as a structured flow graph also. And in that, the forward edges form an acyclic graph where every node can be reached from the initial node G. And the back edges typically consist of edges whose head dominates the tails. And so this is an example of a reducible graph, okay. So you have forward and backward edges, so form an acyclic graph here, and here the backward edges consist of edges whose head dominates their tails. These are the two characteristics of a reducible flow graph. If a particular graph doesn't have this characteristic, then I can call this graph as a irreducible graph. For example, here consider this loop 1, 3, 4, okay. So what is the forward edge? Forward edges forms an acyclic graph, okay. So here if I cut this back edge, 1, 3, 4 will basically form a acyclic graph, and the next one is the back edge consists of edges whose heads dominate their tails. So here this is the back edge, so 1 is dominated by 3, 3 dominates 4, and so on. So therefore this is a reducible flow graph, whereas here it is a irreducible flow graph. Now if you consider there is a loop between 2 and 3, okay, if you could choose the forward edge, and that can be a back edge, the other one can be a back edge. When you remove the back edge, this doesn't result in an acyclic graph, therefore this is not an irreducible graph, okay. It is not satisfying the first property itself, therefore it is not going to be a reducible graph. This is called as an irreducible control flow graph. As much as possible, your structured program should not have an irreducible control flow graph. All the graphs should be reducible. A CFG is well structured and reducible if and only if all its loops are natural loops characterized by their back edges. This is the characteristic. In a well structured control flow graph, there are no jumps into the middle of loop. Each loop is entered only through its header, okay. So you don't have an arbitrary jump is what we are trying to look at here. And a control flow graph derived from programs using structured flow of control statements such as an if then else or a while or a do while or a continue and break are always well structured, and many data flow analysis algorithms work only on well structured control flow graphs. So you should not have an arbitrary go to or a or multiple exits, okay. So if that is possible, so you have to determine whether your control flow graph is structured. If it is structured, then you can adopt the data flow analysis that is possible for any particular algorithm for further optimization. So this is one thing which is additional information. You can have a control flow graph synthesis of some program P named CFG of P is a static abstraction of P in which each node represents a basic block B, and you have edges that connects the nodes such that they represent the control flow from any one of its basic block to its successors. So you can do a synthesis of the control flow graph, and the CFG typically represents a static control flow only, and it does not have to necessarily store which of the two successors in an expression is connected by the true condition, okay, just to have to show two successors are possible, okay. So you need not simulate, you need not show that this is the possibility or that is the possibility. So you do not know which is going to be the chosen path, therefore all we have to show in the CFG is two nodes as basic blocks and have controls to both the nodes. So this is the simple algorithm where you are going to have an address to a particular position PC, and the algorithm creates a new control flow graph node for each basic block, and for each successor S of a basic block n, the CFG build, this is the algorithm, installs a directed edge from basic block n to S. So during this process, each basic block is labeled as reached. At completion, all the basic blocks are inspected, and those that can be unreached are basically taken off, and they correspond to the unreachable code. So output of the CFG build is a pointer to the control flow graph. It has a node whose address will be some PC. Now after this, we are now ready for data flow analysis, which will be handled in the subsequent module. So on to summarizing this module, we have looked at peephole optimization technique, which is an important optimization technique looking at sequence of instructions through a small window, and we have also looked at some basic properties of flow graphs and definitions, which is essential for data flow analysis. So data flow analysis will be discussed from subsequent modules, where we will be talking about iterative data flow equations and global data flow analysis. Thank you.